it is just one long rumble. And you get, if drawn properly, basically a cone here of all these pressure waves building up on top of each other. This is the sonic boom. And the faster you're going, the steeper the cone. So if you're traveling just over the speed of sound, the cone might look like that. And this cone represents where you have a bunch of these circles all overlapping each other. And if you're traveling much faster, it gets to be much more narrow. So this is just over speed of sound. And this is much over speed of sound. And this is, again, how you produce a sonic boom. Now, have any of you actually experienced a sonic boom from an airline? Lived near an Air Force base or anything like that? Or sometimes air shows? It's not, okay. It's illegal without special permission to fly over the speed of sound over the continental US, probably over every country. All right, so recognize also, again, this is high pressure here, that one of the issues that we ran into with the speed of sound early on is that your plane, if you're in a plane, your plane is also experiencing this. It's going to, you have where the engine is, the tip of the plane is not experiencing this issue, but the rest of the plane is, it's hitting these high pressure waves. And so planes, when they first started doing this, the wings basically would fall off. They're not designed for that amount of pressure hitting it. It obviously got resolved. So if you are standing on the ground here and you get hit by this wave, you should feel it at your head first, and then it should slowly move down to your feet. Again, we got this big high pressure right here, so you basically should hear this one bit of sound when this thing passes your ear. Your body should feel it, so this gets into the vibrations part. Your body should feel it, and then it will pass. So it's just when that high pressure wave hits you. Any of you ever cracked a whip? Cracking a whip is another place where you create a sonic boom. So this is just typically the point when we would then go outside and then crack the whip, but that the rules have changed over the course of the past several years, so it's just not happening this semester. Any other questions? I do need to clarify one thing. I talked about hearing a higher frequency. Technically, we don't hear frequency, we hear pitch. I just don't get into that distinction. Some people do. Textbook does. But we hear a higher pitch, which corresponds to a higher frequency, which is actually what's happening to the physical wave. I'm going to grab the textbook, see if there's anything I'm missing, and I think I'm done with 19 through 21. Vibrating stuff, pressure waves, sonic booms, that's all 19. 20 gets into sound. Ah, yeah, I should come back and talk about resonance. Another mistake. And then we've talked about that stuff. All right. So I guess the last bit, there is one more video, so turn this off prematurely. Looks like blinking, good sign. All right, so one of the examples that Hewitt gives for something called resonance is Tacoma Narrows. So let's talk a little bit about resonance. Let's see. Guess not ready for that. All right, so this has what's called a natural frequency. So if I just let it hang here, if I pull it down and pull it up, it will naturally vibrate at a certain frequency. That frequency is based upon the mass and basically number of coils, the spring constant. So if I have more of them, there's a different spring constant, different mass. It has a different natural resonance, or different natural frequency. Now, I can accentuate this. So as this thing vibrates back and forth, and everything has some sort of natural frequency, if I move my hand sort of randomly, it doesn't really change it a whole lot. But if I move my hand so that it sort of matches the natural frequency of this, notice that the vibrations get bigger and bigger. There's a classic example of a bridge in France and soldiers marching across it, that the bridge has a natural frequency. The soldiers were marching in step to match that natural frequency, and the bridge ended up collapsing. From my own personal experience, there was a bridge in Richmond, Virginia. It didn't collapse, but bridges have these sections like this to account for expansion and contraction during winter and summer. And so when you go over it, you hear that thump as your tires go over these. And I'm assuming most of you have gone over a bridge at some point and you've heard that thump. Okay, we got a couple people who nod. Well, they happen to be spaced to the point where you hit the first one and the car just starts rocking a little bit, and it hasn't stopped rocking by the time you hit the second one. And it happened, if you're going just the right speed, you get the boom, and then the next one you bounce a little bit more than you did the first one, and then by the time you get to the end, you're bouncing a little bit more than you would had just been on a regular road. Not enough to cause the car to fall apart, but enough for my personal enjoyment and when I was a kid. There was also, when I was at Duke, one of the engineering professors talked about a business that was in downtown Durham that wasn't doing well. And they did a survey and people didn't have any problems with the store, but after a while they realized from the people who were going there that the people seemed to feel a little bit sick every time they went to the store. Not enough to throw up, but just enough to feel just a little bit off. What they eventually realized was the human stomach has a certain natural frequency. The building itself, as you walked on the floor, it caused vibrations which were close enough to the natural frequency of the normal human stomach. And so as people walked around, the stomach just sort of sloshed just a little bit more than usual, and people felt a little bit sick every time they went into the store. So they changed the natural frequency of the store by putting in extra supports and solved that problem. So, questions to hear before we talk about Tacoma Narrows? All right, so there is a classic example in a number of physics textbooks, this is not Hewitt alone, which talks about Tacoma Narrows being an example of hitting resonance. It is actually not, but it's still worth watching if you've never seen Tacoma Narrows. Just have to get the right video. It's a different physics principle.
of the fundamental jobs of an engineer is to compare loading conditions to strengths.
Yep.
If the loads exceed the
That is not the one I wanted. All right. And Joanna, if you'd be kind enough, thank you. You didn't realize this was your part of your exercise today. So our wind is whipping down through the valley there and hitting the bridge, causing it to do that. See the person on the bridge? Right there. He's walking down the center. If you notice the thing is, as it's vibrating, the center's not moving as much. So this is as close as you get to a node on this one right here. This is the node, and he's walking along the node. Where's
How
this?
is that so flexible?
How is it that flexible?
Yeah.
Well, it has a limit to it, but I mean, asphalt does have some stretch to it. Asphalt's not rock hard. I'm not quite sure of the full details of how they got it that flexible. I assume that there are fewer rocks in there than most pavement, but I don't know for sure. All right, so it did collapse, just some historical bits. It collapsed, I think, within a minute of the professor actually getting off the bridge. And I can only think that he was strolling casually off the bridge because he was not expecting it to actually collapse. The dog did not make it. He was too freaked out. Now, why the car got that far onto the bridge when they finally thought, you know what, perhaps we should get out of the car, I'm not sure. But they knew the high winds would come up and it would sway some. It was built to handle some of that sway. So occasionally it was closed, but apparently not soon enough. The bridge had been open for a couple of months when that happened. Now, why is that not resonance? Or if it were resonance, what would have had to have happened? Let's think back to the slinky. In order for me to get this swinging with greater and greater amplitude, what would I need to do?
Move it.
How?
The same way that it's going.
Say it again?
The same way that it's already going.
Okay. So I need to match my input frequency here has to match the natural frequency. So if I start going with the same frequency as it has, or at least some multiple of it. So therefore, what would the wind have to do in order to create resonance?
Match the frequency.
So it would have to have a gust of wind, the bridge would start rocking, there'd be another gust of wind, it would rock more, another gust of wind, another rock more. I've never experienced wind that goes with a frequency. It's usually pretty constant when there's a wind. So this is actually not resonance, but an example of the fluttering effect. If you take a piece of paper, another pre-COVID demonstration I would do, but take a piece of paper and you blow across the end of it, if you blow just right, the end will sort of do this maneuver. That's what's happening here. The wind was constant enough, it got the other side of the bridge to vibrate up and down, and it was a long enough duration that it just get more and more. So, Tacoma Narrows. There is a new bridge there now. So, but there hasn't been any collapse like that, so I guess they figured it out. All right, any questions about the waves before we start talking about electricity and magnetism? All right, so let's flash back to the atom. We have a nucleus here. And what goes into the nucleus? I heard it faintly there, but protons and neutrons. And what's hovering around-ish? All right. Now the electrons are small, they are farther away. It's easy for an electron to get stripped away, especially in wintertime. Most of you have experienced this at some point. You shuffle your feet a little bit too much over the shag carpeting, or I guess a little bit rarer now than it used to be. But you shuffle your feet, or you're getting out of the car and you've got sort of a cloth seat, and you get that static charge. And you touch the side of your car to pump gas and you feel that shock. Those are electrons being transferred. So as the electrons move, you create something known as current. So technically it's any moving charge, but 99% of the time it's the electrons moving. So moving charges create current. I guess electric current officially. All right, so let's just start out with the symbols, because everybody likes symbols. No one likes writing charge. Yeah, I'm just gonna make that statement. I'm gonna be bold about that. So the symbol for charge, as you would expect, is the letter Q. Why not? So lowercase q would be the symbol used for a single charge, and uppercase Q is for a collection of charges. There's, of course, a force between charges. So, what do you know about the force on charges? Not looking for a formula here. What do you know about, or I could have opened it with, what do you know about charges? Besides electrons are negative, protons are positive, neutrons are neutral.
Positive and negative attract each other. Positive and negative charges attract each other.
Yeah, opposites attract. All right, so opposites attract, and like repels. So one of those golden rules of electricity and the other one I mentioned, 99+ % of the time. If a charge moves, it's the electron. Keeping these two things in mind covers an incredible amount of the next several chapters. Now, there are certain things where things will travel easily, certain things where they will not. So we get into insulator. First, conductor. Insulator. Just a Q does, for an insulator, does not move easily. Ideal insulator, they're not going to move at all. Charges are fixed. For a conductor, charges move easily. Now, given enough oomph, you can get charge to flow through pretty much anything. So there's no such thing as an ideal insulator, and there's no such thing as an ideal conductor. You potentially can make an argument for superconductors where there's no resistance whatsoever, but it takes energy to create those. So if an insulator, things do not move easily, so let's bring out the Van Graff generator. What the heck? What do we have around here that can get fried? I have no idea if that can get fried from it. We'll put that farther away. I think the phone's far enough away, I hope. Now, to turn this thing on and off, it's helpful to have a switch over here. Something that I can turn on and off with my foot. There are some grounding issues with this, and I have shocked myself more than one occasion using this. Apparently that on-off switch does not work. I should make a note of that. Now, potentially this is still charged here. If I get close enough, it potentially could zap me. What's happening here is in a typical Van de Graaff generator, the electrons are basically being stripped from it. So they're, felt that one. All right. So it has an absence of electrons here. The electrons, or plug that in. All right. I was placing the belt years ago, lost the screws. I don't know where they are, but it does make this part rather convenient. All right, so you have a little bit of a felt material right here, and a belt that is just a little bit loose. So when this turns, there's going to be a quick rubbing of it, and what's happening is that the electrons basically get scraped off the belt, making the belt positively charged. The belt comes up to the top. So you have this positively charged belt there, which is then going to draw the electrons from the metal here, because metal is a nice conductor. The electrons get drawn. They will jump from this metal grating right here onto the belt. So you'll have electrons onto the belt. When the electrons get down to this side, they will jump off the belt onto this, making the belt positively charged again, and then it will keep taking more and more charges, negative charges off of this. I've done this demonstration many times. I will tell you, doing it in this time of year is so much better than doing it in the summertime. Let's turn that off. Plug that in. All right. A little bit better light show with the lights off. And that is set on 100%. All right, so right now electrons are being pulled from that. It's positively charged. It's looking for electrons from somewhere. If I put my hand there, it's going to pull them from me. But it's going to pull them from this right here. And you can see the electrons jumping. Okay. I think that belt is about to go. And so once this becomes, once the wand becomes positively charged, because it pulled electrons, because that pulled electrons from here. Once this becomes positively charged, then if I touch it to myself, I would shock myself. Now, in the summertime, when there's enough humidity in the room, basically water is a polar molecule that it will reorient. There's a positive and negative side. It's going to basically stick to it. It's going to neutralize it. And so in the summertime, this demonstration works horribly. And by now, there'd be absolutely no charge on this at all at this point. But I think there is still going to be some. There we go. And then now this is charged, and we can discharge it by touching something metal. Nope. All right. Look at the belt. It's making strange noises, but it does not look like it's really doesn't look like it's as bad as it sounded. No. Now that metal grating that we had in there for the electrons to jump, you wanted to get it close